Good morning. How are you all doing? What, two people over there, that's great. Well, I hope you're still awake. So emerging technologies in carbon capture and storage, hydrogen, offshore wind, it's part of climate change. And really, this session is about the opportunity that is at hand and the skills gaps and where geoscience fits into those skill gaps. I think there's never been a greater opportunity for you all in this day, in this time. We're at the crux, and also I think it's also important to bear in mind that we are part of a much bigger picture. The world is an ecosystem, and we all play a vital role in what we can do. So we all have to wake up in the morning. It's a question I faced. I studied basically oil and gas, converted into carbon capture and storage, because I really wanted to help answer the question about how future energy generation can occur, but also how I can make a difference. So this is a great way to be part of this event. And I hope you understand a little bit more of your career pathways. So a bit of background, I'm currently working at ERM. I'm subject matter expert in carbon capture and storage for ERM. I'm part of CCSA nominated rep. Also in terms of ground modeling in offshore wind, it's something that I'm passionate about. I'm the ex-product owner of high frequency seismic conversion and synthetic CPTs, and bringing in AI and machine learning into the digital space. And I've helped out with JawSoc for a few years. Background in carbon capture and storage. I did a master's when it just came out, good 13 years ago, and BSc in geophysics. So essentially, I'm going to be talking through why do we care about green technologies, and what are the emerging green technologies? What is CCS? What is hydrogen? What is offshore wind? Why, crucially, are you listening to me? What can it offer you? And how really can you capitalize on the opportunity? So let's look at the problem. Right. So IPCC, International Panel of Climate Change 2023 annual report. What you can see is a graph. It talks about the greenhouse gas emissions. Specifically, what you can see is the dramatic increase since 1960 levels. And in the dark blue, you can see the massive contribution from CO2 from fossil fuels. And what does that mean? An increased impact from greenhouse gas emissions leads to increased concentrations of greenhouse gases in the atmosphere. So let's look on the right-hand side. We can see there's a correlation between, on the left-hand side, the increased amount of greenhouse emissions and the impact in the atmosphere to do with carbon dioxide and the purple methane and nitrous oxide. So what? Well, if you look at where the green arrow is, there's a graph of the global temperature. And what we see is since 1960, 1970, there's been a dramatic increase in global temperature annually. And this really drives I guess, where we go as a planet and the innovative technologies and the solutions going forward. And also the role in which geoscience and geoscientists and the skills gaps, what does that mean? So this is a kind of crazy little diagram, but it kind of talks about how in the top right, it's on the bottom there's time, and where we are at present is the black line. And then what you can see in the green line is ideally where we would want to be if greenhouse gas emissions were massively reduced. So you've got low emissions, you've got reduced impact on climate, and you've got equity and justice. Towards the red arrows, the bottom side, you have high emissions. That means increased climate risk, reduction in opportunities for development, and ecosystem degradation. All of these play a part for a story, and a story in time and where we're at, and a story in time in which technologies are now changing, adapting to not obviously going down to that negative pathway. The more time that abates before making massive changes, the bigger governmental policy which will become drivers to these green technologies. The quicker that happens, there's going to be a skills gap, and where geoscientists need to fall into that. So bringing it into emerging green technologies, again from IPCC, there's a typo there. And this is for ideal versus for actual. So what you see at the moment is where we're at, and the current technologies really which are out there to do with pre-COP26, the commitments which have been made by governmental policy worldwide leads to that red box. And the idea is we want to avoid that because we want to be under 2 degrees warming, ideally under 1.5 degrees. The orange here is saying, oh, sorry, the purple here is saying, well, look, if we leave it for a bit of time, but then make dramatic changes in technologies, then we could just about avoid it. And the green and the blue box here is saying if we were significantly to reduce reserves to remain under 1.5 degrees. This is the story that we're in. This is a story you're studying. This is a moment in which these government policies will drive opportunities for you and whether you align yourselves towards that. Okay, now let's look at the green technologies that are here. Again, this is from IPCC report, and it's talking about how manufacturing can largely decarbonize, but switching to things like circularity, switching to zero emission greenhouse gas fuels like hydrogen. And then cement processes can be reduced by using carbon capture and storage. And on the bottom right, it's just talking about how it's just a demonstration of the net reductions in terms of gigatons per CO2 per year. And really, we're looking at, I'm going to be talking a little bit more about wind, CCS, and you could say reduced methane and coal, oil and gas, equivalent to other carbon neutral or carbon zero fuels like hydrogen. And here we see the market cost. I like a bigger picture, and then I'm going to drive it down. Don't worry, make it more relevant. So bigger picture is just saying, look, the efficiency and the cost has been too much to really drive innovation and development. But in terms of solar, wind, onshore and off, you can also see the orange there, and this orange line And where the blue line is below that, then they're already becoming as cost efficient as your fuel or your hydrocarbon fuels here. And what you can see is the market adoption as well, particularly since 2008. You can see the massive drive and increase in, and really what I want you to take home is there's almost like a exponential curve in terms of industry, and there's also an exponential curve in terms of opportunity. So let's talk about these technologies a little bit more detail. You might not be familiar. So carbon capture and storage essentially is capturing carbon dioxide from a point source emitter. You might have a monoethanoic amine solution that captures it at a power plant, condenses it into a supercritical liquid, pumps it on a pipeline and injects it into a reservoir. And a reservoir needs to be at least 800 meters, says a kilometer here, ideally. And really that allows CO2 to be sequestered under the ground for geological time periods, so not going into the atmosphere. But in terms of the skills and the thinking, what is needed to make sure that that CO2 doesn't come out? Well, you need to think of a measurement, monitoring, and verification plan that connects the atmosphere, the biosphere, the hydrosphere, the shallow subsurface, and the deeper subsurface. All those skills and all those technologies need to be considered and are going to be needed. So basically, an MMV plan from the deep to the sky. And in terms of, this is from the Global Carbon GCSSI Institute 2024. The latest report is basically showing here with time, but really since 2024, there's a massive increase projection of CO2 storage up to about 37 mega MPa of CO2. But that is projected to increase by 2050 to 120. Okay, let's talk about offshore wind, something you might be a bit more familiar with. This is from 4C Offshore Wind, and it shows the global outlook. This is from 2019. There was an anticipated pipeline of 168 gigawatts by 2030. And really, the UK ambition is for 30 or 40 gigawatts by 2030. The thing about wind farms is they're not sensitive to fluctuating oil price. There's a long lead-in time. There's several geotechnical campaigns and geophysical campaigns, and they utilize the next generation of seismic processing and seismic imaging techniques. The latest update at the moment, and really what I want you to take home, is just saying that the different variations of green is where there's going to be more commitments to wind globally, but particularly in China, Europe, UK, and as well as Germany, that have made significant commitments, and where the industry is vastly growing at a significant rate. So let's understand what happens on wind farms. Initially, you have your desktop study, which is just using preliminary public data to understand the ground conditions. They want to maybe see, is it justifiable? Can they progress? Now you move on to a preliminary geophysical survey to get a better understanding on the ground conditions. Line separations are pretty large. And then you do ground truthing. So you're understanding geologically what the layering is and you need to now connect it with geophysical lines. I put in seismic inversion there because that's a new technique which is coming out in terms of digitally using machine learning and coding to utilize those ground truthing as well as seismic lines to better understand the ground conditions in a 3D sense in a quicker way. And then you've got detailed geophysical and geotechnical surveys leading on to your engineering design parameters and your ground model, and then your installation once you've understood the ground in 3D domain fully. So in terms of site investigation, typically you have, it's non-intrusive methods. This is geotechnical site investigation, for example. You have different probes for different reasons. Here in the top right is what's called a CPT, cone penetration testing equipment. There may be also, when you drill into the ground, you take samples and you do analysis on those samples and testing on those samples. And then you're going to be correlating to the geophysical data seismic lines as well across the site and building up a picture. You're taking different sampling extraction methods from the vibrocore, which is on the very right-hand side here. You've got box corers, grad samples. A vibrocore can go down to about 6 meters, and you can get samples, and then you're logging it, whereas a grab sampler is only about 0.3 meters. And the CPT, which is a quick and efficient way of collecting lots of data about the ground truth, but on a boat, usually when it's evidently offshore. And again, it's just building this picture of the ground and the ground conditions. On the left-hand side, you've got borehole geophysical logging. On the right-hand side, this is actually inside a lab on the back of a ship. So they're doing soil logging and they're doing a bit of geotechnical testing as well. So in terms of hydrogen here, essentially, you're taking the excess amount of energy that has been acquired from wind, and then you are using through electrolysis, creating hydrogen, and you're storing it. And you're storing it for a time that energy demand is needed at a later point. So it's flexible, it's secure, it can be used as an alternative fuel source. And it just creates a lot of opportunity there. It's for cheap and safe energy production. Here an example, there's different ways of storing it at different depths, possibly lined shafts, lined rock caverns, salt caverns is also a great option in the UK, and old oil and gas reservoirs or depleted aquifers as well. And just to give you an idea, in a salt cavern, a small cavern, you could have approximately maybe a few hundred different caverns in just one salt diapir. And 5,000, just 5,500 tons of hydrogen gas is equivalent to up to 1 million hydrogen-powered cars. And just to give you an idea of scale, you've got one small cavern here, and that's almost the size of the Empire State Building. Okay. Geoscience skills gaps. So I'm just going to read this verbatim. It's a paper, I've referenced it, from Hollis et al. And they said, qualified, knowledgeable geoscientists are needed to tackle multi-Earth system-related climate changes, including water security, supply of minerals, low carbon technologies, development of renewable energies, and carbon capture and storage. However, global geoscience student numbers have been in general decline for almost a decade. And right at the bottom here is a great point. The dilemma is that more geoscientists are needed to limit climate change within the decade, but young people do not recognize geoscience as part of the solution. In other words, there's a great opportunity, there's a great skills gap already, but that differential is going to get significantly larger. Now, this is just an example of all the different skills that might be used in CCS, offshore wind, hydrogen, and I'm just going to reel off a few, but you can get a general picture from geologists, geophysicists, like seismic processors and interpreters, engineering geology, hydrologists, geotechnical engineering, wireline logging, reservoir engineering, ecology, consents, geochemical, GIS. This isn't even an exhaustive list. So what is the key ways you can capitalize on this opportunity? Start off with your CV, we already heard in a previous session. Highlight key achievements, but key skills relevant to the jobs. Update LinkedIn, build your network. Align your dissertation, wherever possible, to an industry problem and try and maybe get a work placement or internship. Also think about specific softwares that industry are using. So in my industry, geophysics, you're thinking Kingdom, Petrel. Try and align your dissertation towards that. It already gives you a step ahead of the game. And as I said, even if you've only got 3 or 4 weeks, make sure that you try and get some work experience under your belt. And as a previous speaker mentioned, coding is key. Try and think of what can set you apart. And then finally, be part of a industry recognized organization, such as the JOLSOC, become a member. Okay, thank you. And just to say, if anyone wants to stay connected and build your network, you can connect with me on LinkedIn and links for current vacancies.
Wonderful. Thanks very much, Benedict. I think we have time for one quick question, if there are any. We haven't had any online, so if there's any in the room. Okay, no, well, we'll just say thanks again. And you'll hear that people can come and chat to. Yeah, wonderful. Thank you. Okay, so next up we have David Schultz from the University of Manchester.
Okay, great. So while he's getting that set up, my name is David Schultz. I'm a professor of synoptic meteorology here at the University of Manchester. And you may be wondering why I'm speaking at this session. As you'll see when we get to the slide on my career history, I actually started out as a geologist as an undergraduate, and then went and got my master's and my PhD in atmospheric science, and that's where I've spent most of my time since then. Thank you. So here's kind of my career path. I was at MIT as an undergraduate, and although I was a geology undergraduate, I took a lot of different courses from a lot of different earth sciences, engineering, hydrology, and so I feel like I come with a little bit of a broader background than most undergraduates in geology itself. As I said, I went on and became a meteorologist, and after that I worked at the National Oceanic and Atmospheric Administration Research Lab, the National Severe Storms Lab. That's where they chase tornadoes. Came to Europe in 2006, where I worked at the University of Helsinki and the Finnish Meteorological Institute, helping them bridge the gap between what their researchers were doing and what forecasters were doing, and help get more research ideas of the products that they were doing into operations. In 2009, I came here, and by 2012, it started out as a part-time position, and eventually I became full-time, and it's eventually reached the reader, started out as a reader and then eventually became a professor. So my research interests here in the Department of Earth and Environmental Science have become immensely broader than kind of the narrow interest that I had in high impact weather, in convective storms, tornadoes, snowstorms, and that kind of stuff. And some of the tools that we developed here, both for teaching and research, include ManUnicast. It's our daily forecasting system for weather and air quality. Anyone can access it, and if you have an iOS system, you can download the app. Because University of Manchester is so large and our department itself is quite interdisciplinary, I started doing a lot of other things, looking at the effect of weather and health on things like COVID, on pain, Legionnaire's disease. I've also been working with engineers on ocean and wave modeling, and even people in our own department on glacier modeling as well. But what I want to talk a little bit about is kind of the bridge here between a previous speaker who was talking a lot about the current and future climate and how we can address that. I want to go back a little bit in time and talk a little bit about paleoclimate modeling and climate modeling in general. And that's where a lot of my expertise has developed here. And that's the value of being in a large university with a lot of different topics, as well as in a department that has forced me to expand my research interests. Again, this is a tool that we built. Anyone can access it. It's called Build Your Own Earth. And what it does is it arose because I had a desire to show people the kind of things that we were doing with climate modeling. You know, everyone talks about, well, what's the climate going to be like in the future? Well, the primary way that that happens is through modeling, through climate modeling. But the general public, students don't necessarily have access to the output of climate models to see what they actually look like. So that's what this was all about. You go into Build Your Own Earth. You can select from a number of different types of Earths. You can select a range of different kind of Earths under the current configuration. Paleo Earths, there's some really strange alien Earths, like what if the planet was covered all in ice, for instance, or all covered in water? What would the circulation look like? What would the temperature, the precipitation look like? And so you can select from about 60 different climates, and then you can plot, I think, 60 or 70 different climate properties on that. And so here's the simplest one. Here's the current day Earth. It's actually 2015, because that's when we built this tool. But you can see here's a static snapshot of the global monthly average temperature in August. And you can plot it a number of ways, or you can put it in motion and see it evolve over the course of the year. But as I mentioned, we not only do current Earths and current configuration of Earths and future Earths, we also go back into the past. So here are two snapshots of precipitation rate, millimeters per day, both in February and August in the Jurassic, 170 million years ago. And you can see features that are very similar to current climate on Earth. You can see the blue intertropical convergence zone. Well, thankfully that's still there, and it moves with the sun over the course of the year. And you can see the deserts in the central parts of Pangaea as it is breaking up during this time, both north in the subtropics and also south in the subtropics. And why I show this is because we completed these simulations, and one of the geologists in our department who was working on his PhD was like, hey, you know, I'm studying this field site. You can see the white box here in South America. You know, we've seen these unusual formations. Can you tell me about them? And we're like, well, let's see what we can learn from the climate model output. So what they found were meters and meters and meters of these deposits that alternated between interflood and river flood periods. And I think, whoops, nope. And what you see is very large grained, fast moving conditions as opposed to very silty, thin conditions. And what we did was we looked at this and found that it was a result of the motion of this subtropical drought from throughout the year, producing cycle after cycle of these interflood periods. So this is an illustration of how you can use field geology and merge it with the output from these climate models. And that work was published in the journal Earth Interactions, showing how we were able to, again, link across this using different methods to help Marcello and his team understand this, this formation a little bit better. I had a couple of master's students who wanted to do a climate modeling project, again, using the same climate model that we did. And so they had the idea, well, let's look at Snowball Earth, the one that happened about 2.4 billion years ago. And let's look at the effect of mountain ranges on this paleo supercontinent. Now you can imagine that almost 2.5 billion years ago, we probably didn't know very much about the structure of the continents at that time, but the reconstructions that had been done suggested that there was a supercontinent that was kind of assembled more or less centered on the equator. And so what we did, what the students did, was put a mountain range on the equator, or every 10 degrees away from the equator. So one at plus or minus 10 degrees, plus or minus 20, all the way up to plus or minus 50. And then we ran one where there were no mountains at all. And so then, of course, we didn't know how much carbon dioxide, methane was in the atmosphere at this time. So we made some reasonable guesses for that and tested for a range of conditions, both we fixed the carbon dioxide concentration and then varied the methane concentration. That's the x-axis in this plot. And then we varied the location of the mountains. That's the y-axis of the plot. And for each of these, there's 50 different simulations or so. We ran it to equilibrium, and there either was a snowball Earth, in other words, the model totally covered up the planet in ice and snow, or it produced polar ice caps that left the tropics, subtropics, and mid-latitudes free of ice. And you can see that there were quite abrupt transitions, and you know, it was either ice covered or it wasn't ice covered at all. There was no kind of in between. Well, it was like ice covered. That never happened in the model. It was very definitive, very sharp. And, you know, what we learned was that there was no simple, well, just move the mountains towards the equator and you get certain kind of result. But anyway, it shows you kind of the things that we can do to explore the Earth in different scenarios. One of the things that we noticed about these simulations was how rapidly snowball Earth happened. If you were able to maintain ice well away from the equator, say outside plus or minus 30, 40 degrees latitude, you would never form a snowball Earth. But the moment that you got ice within about 20 degrees of the equator, that's it. Within decades, that would close up. Each one of these lines in these graphs is a 10-year average. So literally within 10 or 20 years, the temperature drops substantially near the equator. The amount of precipitation shuts off at the intertropical convergence zone because there's no sea surface anymore. And of course, the amount of snow and ice covers up as well. And it's very abrupt. It's very abrupt. And I think that's one of the most shocking results. We talk about geologic timescales, and even when we think about the ice age, things happen thousands of years. I mean, this is 2 orders of magnitude less than that. So I want to talk a little bit about the landscape that's out there for climate and paleoclimate researchers. And again, I'm going to come at this mostly from my modeling perspective. If you go to the Geologic Society webpage, you'll see this Geology for Society. And I found this very useful to communicate with my students about the kinds of career skills that they can have in earth and environmental science, the kind of career options that they could have. And I mean, you can see geology for the economy, energy, water, and you've heard some of them, and we'll hear some of them later today. But if you scroll down, eventually you'll find one for climate change. And that can be, and it opens up and gives you a bunch of resources, talks about the kinds of careers you could have in climate change. Very useful. One of the things I want to point out, and this may be of use to you if you're thinking of a career in climate or paleoclimate, is this article. It's actually a statement that the Geological Society published. I was a co-author on it. And what I like about this and why I'm recommending it to you is that it kind of brings together in a concise statement why geology is important for the present and future climates. And drawing upon what the past climate tells us about this. And so I'm not going to go into it a lot of detail, but just this one graph here, I think is quite illustrative. So we've got kind of the origin of this graph is set at pre-industrial levels, amount of carbon dioxide in the atmosphere versus the atmospheric temperature. And if you look at the trajectory that we're headed in upward and to the right on this graph towards the Pliocene. And if we don't stop emissions, then we could end up simulating, we could end up being in a climate that is similar to that existed in the late Paleocene or the Eocene thermal maximum. Paleocene, Eocene thermal maximum. So anyway, those are, that gives you some context for that. And in order to understand these past climates as kind of analogs to the future climates, we need not only climate modeling that I talked about, but field research, laboratory work, all of those things can be used, all of those skills can be used to help put what is coming up in the future or what we could avoid in the future if we take action this way. And again, that's why I like working in an interdisciplinary department. I get to talk with people who do this stuff. I don't have particular expertise myself, but it's that blending of the modeling, the field work, the laboratory work that all comes together. And so what I want to do is end on, again, like previous speaker did, talking a little bit about thoughts that I've had about my career and what you could do to help prepare yourself. And I think one is kind of about organizing and centralizing, not centralizing, but putting a focus on yourself as a conduit for organization and ideas and things that you want to develop. And I'm coming at this mostly from an academic or a research point of view. The other speaker in this session obviously gave you a perspective very heavy on the private sector, and there's nothing wrong with that. But if you like kind of the academic side, the research side, even if it's in a research lab and no particular affinity for being an academic, then being organized about your workspace, your laptop, is essential. Keeping a set of ideas in your head about, okay, well, here's where I could go next with this, or if I change jobs, these are kinds of things that I could be doing. I think it's also important to challenge yourself and put your ideas to the test at every possible stage. So giving seminars locally within your university, or even if you go back to places where you graduated previously, say, hey, I'm going to be in town. Can I come and talk about my latest work when I'm in town? Using informal peer review of your friends, your colleagues, your office mates is a really critical step that I don't think we do often enough. And I raise my hand on that as well. You know, getting ideas, bouncing ideas off, getting feedback from people is, well, it's one of the ways that we learn. And if we're not taking advantage of that, we're missing a trick. And just even having a student-led reading group or writing group, everyone's got to write a dissertation at some point, right? Just get together for an afternoon once a week, sit down and all share your writing experiences, and then spend the rest of the afternoon writing together. You can order in pizza or whatever you like. I mean, you can set it up a number of ways, but again, I think it's an important skill, not only for you know, building camaraderie, but you know, starting to work on building your personal network, and then of course developing those skills and sharing ideas amongst each other. I don't mean to sound crass, and certainly I don't use marketing in kind of the crass commercial way, but it's about selling yourself as this is who I am and this is what I do. And so having a web page where you talk about what it is you do, being on LinkedIn, maintaining a blog, you know, you don't have to be on every single social media channel. And, you know, if you don't want to do that, that's fine. But at least think about who are the colleagues, who are the people, who are the fellow students that need to hear about the work that I'm doing. And so when you get to a point where you're going to, where you've published a paper, you know, emailing it out to them and saying, hey, look, here's my latest paper. I'd like to hear your feedback on it. You know, going to conferences regularly, maintaining the links with the professional society, all really important things that I found in my career have helped me, I think, achieve more than I would have otherwise. And then finally, thinking about your career skills, particularly in the planetary science, the idea of data science and how computer skills and plotting and analyzing data has changed so much. It's not good enough just to know Excel anymore in your toolkit for data analysis. Knowing things like Python, IDL, MATLAB, these are going to be tools that you can take forward with you and then use to build better tools. Oral presentation skills, writing, posters, these are all important ways of distinguishing yourself from other people. I would like to think that when I was fresh out of my PhD, I had a lot of opportunities, invited speaking positions at conferences or meetings, invitations to apply for jobs at various universities and so forth. And, you know, one of the things that was apparent to me was because I was getting those invitations because of my desire to publish and making sure that I wrote good papers and published good papers, but then also gave good presentations at conferences better than the average. So you can reflect on that and the kind of skills that you need to develop from that. And then, you know, also teaching skills, mentoring skills, consulting skills, and then just general building your own personal network. These are skills that I found that many students, I think, undervalue in themselves, and you know, making a more concerted effort to put these at the top of your CV, I think, can be very effective. And I think, right. And then choosing your workplace. If you've got opportunities to pick the places where you want to work, picking the best in the field to go with, people that respect you, gossiping with other students at conferences like this about, hey, what's your university like? How's that department? Who are the idiots to stay away from? These are important things to discuss at meetings like this. And I think finding a workplace that values you as scientists is really important, because that's your brand. If this is the kind of career that you want, then you know, there's some places that quite frankly are not well suited to certain types of people. And you want to avoid those. You want to avoid working with those people. So find the places that do support you as an individual, as a scientist. As I mentioned about broadening your skill set, reserving ideas for your own side projects. If you're applying for a PhD, you know, maybe things are a little bit rushed in a PhD with a 3 or 4 year program, but keeping those idea files going in your back of your head, you know, okay, when I get a chance, I'm going to work on this myself. And my own PhD advisor, I had 2 of them, but one of them told me, when you're choosing a job, choose the one that opens more doors than it closes. And I think that's a pretty good, I think, life lesson anyway. So with that, I'll close. Thank you.